Hello, and today we're talking 4.6, which is approximating values of a function using local linearity and linearization. What an exciting title. What we're essentially going to do is we're going to find our derivative of our position function, or sometimes we're even given the derivative of our position function, and we're going to make a tangent line from that. Once we have that tangent line, we're going to approximate a local value, meaning a value nearby, right? We're not going to go crazy far away. We're going to do a value pretty close. And then we're going to see, is that an over or an underestimate? But first, let's talk about concavity. So if we have a position function, we're going to call it P of t, then we can talk about its concavity based on A of t. A of t, of course, is the same thing as P double prime of t. And we can talk about concavity of two ways. If something is concave up, which would mean that this is positive, this is concave up. Or we can talk about something concave down. And we'll talk more about concavity, but like this is kind of important for today's lesson. So let's try to hit it while we can. So the first one is that it's concave up. This concave up means that we're going to have a positive acceleration. All that means is that the slope is getting bigger and bigger. And this kind of makes sense. Let's look at kind of this chunk right here. We would say that this chunk is going to be concave up. If you look at the slope kind of starts off a little bit negative. And then as we keep going, it starts to get less negative. Then it gets to 0, then it's positive, then it's more positive, and then it's like super positive. And then somewhere in the middle here, it changes concavity, right? So here we say the concavity is up because if we look at that acceleration is positive. And then what happens is now we have this inflection point, which we'll talk about more in the next unit, right? That's unit 5. But what ends up happening is the slope stops increasing and it starts decreasing, right? So a little bit positive, a little less positive, a little less positive. Oh, now it's 0 and now it's going negative. And so we can talk about these two pieces in concave up versus concave down. Okay, so if we're figuring out concave up, that means the second derivative has to be positive. It's concave down if the second derivative is negative. Again, remember, this is also just acceleration. So like, let's say we're given v of t, then we'd be looking at v prime of t as our acceleration. Okay, so just to understand a little bit of difference there, but we're really talking about the same thing. All right, so a tangent line of an equation at any point may be used to approximate the value of a function near the point. We're going to use the Taylor form of the equation. Really, all it means is like this. You don't necessarily have to do that. You can do it in a number of ways. I'm totally fine with my minus y sub 1 equals, I guess let's say f prime times x minus x sub 1. They're using it with a. We should say x prime of x sub 1 if we want to get real fancy. But we're going to use that to make approximations. So here's our example. We're given selected values of a derivative. It is known that h of 4 is 5. So h of 4 is kind of, or h of x is our position. And we're told specifically that we have the position 4, 5. So we're trying to figure out the approximate value of 4.2, and we're going to find using tangent lines. So what we're going to do is we're going to say, hey, this value here is 4, 2, and this is 4 is the x. The slope here is 2. We're going to use this point because we are given this position. We can't use the 4.2 as much as we'd like to because we don't actually know what h of 4.2 is. So we're going to say, hey, y, or we could do f minus 5 equals 2, which again, this is just h prime of 4 times x minus 4. Again, if we want to write that another way, that might be helpful for us. we would say, hey, let's rewrite this as y equals 5 plus 2 times x minus 4. That also works. And we're trying to figure out the approximation of h of 4.2. So all we're going to do here is we're just going to plug in 4.2. And we say, okay, y equals 5 plus 2 times 4.2 minus 4. And that gives us 5 plus 2 times 0.2, or 5.4. And so this tells us that h of 4.2 is approximately 5.4. Now, we might use something like this if we're dealing with, again, we want an approximation. This isn't asking for an exact value. Maybe the function's really gross to deal with, and it's easier for us to find a derivative really close by hand and say, hey, is this kind of close? Sure, right? Would we ever use this if we have the actual function and we just want like the exact value? No, but it's again good for specifically approximations. Okay, so let's talk about justifying over and under approximations. Let's say that f of c is approximately t of c, which is equal to f of a plus f prime of a times c minus a. So c is the value we're plugging in for our function, or the value not we're plugging in, but we're trying to figure out. So we're talking about this being concave up on this specific interval, right? So on this interval a to c or c to a, either one we're dealing with, if c is before or if c is after the actual tangent line we have. Notice if it's going to be concave up, that means we're going to have a underestimate. If we were going to say like plug in, let's say this is the point we want to find our estimate of, and we do our tangent line, we can see that if any value either to the right or to the left, that our tangent line is actually going to be an under approximation. So what we would do is we would say, hey, here's our function, right? Here's our position function, or in this case, this is a kind of a velocity function, right? But let's assume this is a position function. We say, hey, this position function is totally concave up. No matter how we draw our tangent line is always going to be underneath this curve. So if I'm doing a local point, even like, just a little bit away, either way, it's going to be an underestimate. Whereas if we change this to somewhere where it's concave down, for example, something like this, if I have my tangent line at that point, any point even close by is going to be an overestimate, because our line is always going to be above this concave down curve. And so the big takeaway here is that when we're dealing with this, if it is concave up, we're going to have it be an underestimate. If it's concave down, then our piece is an overestimate. Let's look at a problem. So here's my position function, and we want to write a tangent line when x equals 3. Then we're going to use this tangent line to estimate the value of the curve at 3.1, right? Locally, we're not going that far from 3. Could be even closer, but we're going to just do a kind of close estimate here. And then we're trying to figure out if this estimate is an over or underestimate. So we have 2 points, or two kind of parts to this question, really 3 parts, right? First, tangent line. Second, what's the value at 3.1 using this tangent line? And then third, is it an under or is it an over? So if I'm going to figure out this tangent line, the first thing I need to do is figure out what is f of 3. So I have f of 3. I'm going to put it into my function. We're going to assume here you either have a calculator or 3 is really easy to deal with. I think either one of these things is true here, but either way, we get 61. So this is kind of my coordinate that we're dealing with. And then we need to find f prime of 3. So I first say, okay, well, what's f prime of x? F prime of x is 3x squared plus 10x minus 6. And so now I'm going to plug my 3 in. If you want to do this all in one step, that's totally fine. Just make sure your derivative is correct. Otherwise, you're going to have a bad time. So that's 27 plus 30 minus 6. That gives me a slope of 51. My goodness. So this slope is 51. From there, we need to actually write our tangent line. So this would look like y equals, or we can deal with f of x or whatever you want to really deal with here. 51 plus, oh, sorry, my bad. It would be 61 plus 51 times x minus 3. So notice this is my slope. Slope, if some reason won't write, slope, okay, now it went to black for some reason for 1 second. Slope, this is my y value, and then this is my x. That's supposed to be a y, but it doesn't want to draw a y. From here, we say, okay, here's our equation. We've done the first part. We've written the tangent line. Now we need to figure out, well, is this going to be a, well, what's the estimate at 3.1? So now we're going to plug in and say, hey, f of 3.1 would be, actually, I don't want to use f because this is more of an approximation. We can use our approximate symbol. We could just say y equals, I'm fine with either one of those. But 61 plus 51 times 3.1 minus 3. And so 61 plus 51 times 0.1 gives us that f of 3.1 would be approximately 66.1. Now, from there, it asks us, is this an over or an underestimate? So what I need to do is I need to figure out what's going on this interval. Is it going to be an over or is it going to be an under? Meaning I'm looking at the concavity. And so we're going to find the second derivative of f of x, which would be 6x plus 10. And we can see if we plug in our either 3 or 3.1, but in this case, let's just say, hey, we're going to plug in 3.1. We'd realize that f of 3.1 is positive. And so what this means is that our function is concave up. Our line, whatever we're dealing with, was something like over here, kind of past the vertex of this, quote unquote, vertex of this curve. And so we'd say that this is an underestimate. If we want to give any type of reasoning, we would just say, hey, it's an underestimate because our function is concave up. All right, try this one out. Pause the video and try and see where you're at. Okay, so same function, right? So we still can use f prime of x and everything that it is, which is literally just 3x squared plus 10x minus 6. And now we're trying to figure out the tangent line at -5. So f prime of -5, we're going to plug that sucker in. That's going to be 75 minus 50 minus 6. And so that gives us 19. So the other piece we need is obviously f of -5, which I'll plug that in. I would 100% want you to have a calculator here. That's -125 plus 125. Actually, I take that back. I lied completely. I'm totally fine without you having a calculator here because this is just 37. The 5s cancel each other out. It's only because those cancel. If those didn't cancel, I'd want you to have a calculator. But we get this following equation. Y equals 37 plus 19 times x plus 5. So here's our tangent line. We're going to use that to estimate what's going on at the curve at -4.9. So we go y equals 37 plus 19 times -4.9 plus 5. And that will get me, I think, 38.9. right? If we do 19 times 0.1 plus 37, we're good to go there. So this is kind of our approximation of negative 4.9. So a little squiggle symbol there. We're dealing with an approximation. If we want to figure out if it's an over or under, again, we're going to do f double prime. F double prime of x is equal to 6x plus 10. And this time, if we plug in negative 4.9, we realize that f of negative 4.9 is going to be negative, right? Because that will be like roughly negative 30 plus 10 is negative 20. And so because this is concave down, we're kind of essentially to the left of the maximum, the relative maximum here. And so we could say, hey, our line's going to be above. This is going to be an overestimate. All right. And then our last piece, multiple choice question. We're told H is a differentiable equation such that H of 4 equals 3. And this is our slope. The graph of H is concave up. So again, this is concave up. So that means instantly our value is going to be an underestimate. So we can kind of get rid of B or A and C because those are both dealing with overestimates. It's concave up for this whole interval, 3 to 5, and we know that our point is in between 3 and 5. Which of the following is a true approximation of 4.3? So we're going to use our function, and we're going to say h of x equals 3 minus 2/5 times x minus 4. And we're going to plug in 4.3. So 3 minus 2/5 times 4.3 minus 4. And we realize that our value, we don't even really have to do that much math here. We just have to realize that our function is going to be less than 3 here. So we say, okay, 3 minus 2/5 times 0.3 is going to be approximately 2.88. And again, we know that this is an underestimate because it tells us our function is concave up. So final answer is D. All right, gang, if you have any questions, as always, feel free to reach out. Otherwise, have a great day. Bye-bye.